Hello everyone, I'm Yihua from Alibaba. I'll represent our team to give a talk on our work, Hidden Inheritance, an inline caching design for TypeScript performance. The novelty of our work is to leverage the static type hierarchy information in TypeScript and generate efficient inline caches to improve the performance of TypeScript, especially for programs of object-oriented programming style. This is the agenda. I'll first give the background and motivation of our work, and then I'll introduce the definition of hidden inheritance and its implementations. Finally, the experiment data will be shown to prove the effectiveness of our work. TypeScript extends JavaScript by adding optional types to the language. It provides robust program abstractions, such as classes and interfaces, for developing large-scale applications, for example, Egret Game Engine, Visual Studio Code, and frameworks like NativeScript Angular and Vue.js. Although TypeScript can speed up the program development by being able to validate the code before running, it does not speed up the execution of the program, as the static types are erased when transpiled to JavaScript. To understand the motivation of our work, we firstly recall the idea of hidden classes and inline caching. We only focus on the hidden class and inline caching design in V8, since the designs in other popular JavaScript virtual machines are similar. In this program, when object A is created, its hidden class field points to an initial hidden class HC0. The HC0 contains no property layout descriptions since no property is added. Next, when a property X is added to object A inside function foo, a new hidden class HC1 is created by V8 runtime to record the new property's layout information in the form of a keylocation pair. After HC1 is created, the hidden class field of object A is reset to HC1 from HC0, and the value of the property X is stored to the location 0 inside A. To reuse hidden classes, V8 links these hidden classes HC0 and HC1 to form a transition tree denoted as TT1. With transition trees, the overhead of creating hidden classes can be avoided when the same properties are added next time. With hidden classes, then we introduce the inline caching mechanism, still in the context of V8. When the runtime of V8 encounters a new hidden class and figure out the location of the target property inside the object, it caches a pair of hidden class and location to accelerate the next loading operations. For instance, as shown in the figure, the runtime would cache a pair HC1 and 0 for the access site in line 5, after calling the function foo in line 11. HC1 is the hidden class of object A and 0 is the location of property X inside object A. If the code in line 11 is executed again, the runtime can directly load the value of property X at location 0 as long as the hidden class of the incoming object matches the cached hidden class HC1. As you can see from this example, inline caching plays an important role to optimize the object accessing for dynamically typed language. On the other hand, if the incoming hidden class does not match the one cached, an inline cache miss happens. For example, when executing the code in line 12, since the hidden class HC4 of object B is not identical to HC1, an inline cache miss occurs. In TypeScript programs of object-oriented programming style, inline cache miss can happen when objects of parent and child classes are passed into the same function for operating, which is a common behavior of type polymorphism. It hurts the performance especially when the inline caches are incorporated into the JIT code and de-optimizations have to be taken in response to the inline cache misses. For example, in this program, since hidden classes of object W and object H are not identical, Inline cache miss happens in line 4 when object H is passed to the construct of class A. Now we have the background in mind. The goal of this paper is solve the problem of inline cache misses in TypeScript program where type polymorphism are very common. To achieve this goal, we would generate more efficient inline caches by exploiting the static type hierarchy information of OOP-style TypeScript programs. Specifically, we implement an inline caching design called hidden inheritance. By leveraging the interfaces and classes inheritance relationship and static types, hidden inheritance can produce efficient inline caches for the OOP-style polymorphic operations. We present the main ideas of hidden inheritance as listed in this table. Among these 4 ideas, the key is to represent the inheritance relationship of classes and interfaces with a so-called hidden inheritance relationship, and then generate efficient inline caches based on this relationship. Before give the definition of this hidden inheritance relationship, we firstly extend the classification of the local property and prototype property to the context of hidden classes. For instance, the local set of hidden class H is the local property of its own object, so does the onProto set. In addition, we introduce the lookup table called vtable, which is a table that is used to cache prototype properties information. The idea of vtable is very similar to one in statically typed language like C++. In this example, we can see that the hidden classes in the same transition tree contain different local properties but share the same onProto properties. For instance, hidden class HC5 and HC6 share the onProto properties, while they have different local properties. Especially, note that as a kind of lookup table, a hidden class's table may not cache all prototype properties. For instance, considering name shadowing by the constructor of class B, the constructor of class A is not cached in the vtables of HC7, HC8, and HC9. After classifying properties and defining the property sets for hidden classes, we can define the inheritance relationship between hidden classes. The hidden inheritance relationship is a relationship between 2 hidden classes A and B, if and only if they satisfy these 4 conditions. The hidden inheritance relationship can be regarded as an enhanced structural subtyping relationship. The first 2 conditions are designed for specifying the consistency of local properties and vtable properties between hidden classes, which is essential for generating monomorphic inline caches. The last 2 conditions are designed to statically specify the locations of properties and remove the overhead of visiting prototype chains in inline caches. After defining the hidden inheritance relationship, we define hidden inheritance tree, which consists of hidden classes as the tree nodes. A hidden inheritance tree not only requires the hidden inheritance relationships between each parent node and its child nodes, but also each leaf node in itself. To realize the hidden inheritance technique, we build a TypeScript engine called Static TypeScript Compiler on top of TSC and Google V8. We call it STSC for short. STSC implements a transpiler which not only reuses the original passes of TSC to parse TypeScript code and infer types, but also encodes these types into some JSON strings. We call these JSON strings as type annotations, which are embedded into the emitted JavaScript code in the form of comments. The emitted JavaScript code is called typed JavaScript. Then, STSC compiles the typed JavaScript programs to abstract syntax trees and attaches the decoded static types to the abstract syntax trees. Next, STSC visits the typed abstract syntax trees to generate hidden inheritance trees as well as other objects. STSC provides two compilation modes to consume the generated hidden inheritance trees, bytecode mode and native mode. They aim to produce bytecode and optimized machine code, respectively. At the runtime phase, the runtime system of STSC loads the output of the compilation phase and executes the compiled TypeScript programs. Now let's talk about how STSC generate the hidden inheritance tree with an example. The program declares two interfaces I1 and I2, and two classes A and B. STSC firstly selects three candidates of hidden inheritance tree nodes, I2, I1, A and B. Then, these candidate nodes are linked into two candidate trees, tree 2 with I1, A and B, and tree 1 with I2. Next, STSC selects the local sets and vtable sets for these four candidate nodes. Note, properties with name conflication are carefully removed during selection to meet the conditions of hidden inheritance relationship. Then, STSC performs a top-down breadth-first visits of these two candidate trees, merges downwards the contents of local sets and vtable sets, respectively. Finally, STSC creates four hidden classes, hidden class HC16, HC17, HC18, and HC19 from the final local sets and vtable sets, and link them to form two hidden inheritance trees, tree 1 and tree 2. With hidden inheritance relationship, STSC can generate efficient inline caches. This example shows the code generation algorithm of STSC for loading properties. STSC first generates two hidden classes based on the two interfaces I1 and I2. When object B with the hidden class created from interface I2 is passed to function foo, no IC miss will be triggered since STSC can detect the hidden inheritance relationship between the two hidden classes and directly load property X from location 0. Note that all the actual loading operations are guarded by the check of hidden inheritance relationship. Based on the definition of hidden inheritance relationship, STSC can enlarge the scope of cache-hitting hidden classes from the cached hidden classes to their descendant hidden classes in the same hidden inheritance trees. To demonstrate the performance of STSC, we select benchmarks from Industry Benchmark Suite Jetstream 2 and real-world applications. All the benchmarks and applications are displayed in the benchmark table. The lines of code indicates the lines of the TypeScript code. Note that the line of code of the four Vue.js applications include the line of code of Vue.js framework. As we manually port some benchmark from JavaScript to TypeScript, the manual types row indicates the numbers of the added static type annotations. The classes and interfaces rows indicate the numbers of classes and interfaces in the benchmarks, respectively. We run and compare the benchmark with four configurations, BB, SB, BN, and SN, as shown in the configuration table. Results reported in this figure shows the average performance for BB and SB. The performance are normalized to BB. The numbers in parentheses are the iterations. We use the original iteration numbers of Benchmark Suite Jetstream 2. The absolute times are shown on the right of the BB bars. We can see that SB can significantly reduce the average execution times of the 6 benchmarks by 8.75%, WSL 15.17%, TSC 17.74%, Grid 15.56%, SVG 20.03%, Tree and 10.21% to DOMK. For other benchmarks, SB does not show notable improvement due to the small numbers of interfaces and classes. This figure reports the average performance of the statically generated machine code of configurations BN and SN, Recall the BN is the native mode of STSC, while conventional inline cache is generated to replace the hidden inheritance-based inline cache, so this comparison is to demonstrate the effect of hidden inheritance relationship for machine code. Note that for configuration BN and SN, we disable the JIT compilation of STSC during the executions in order to measure only the quality of the statically generated machine code. From figure, we can see that SN significantly reduces almost all the execution times by 6% 67%, except for the benchmark error. Finally, we give the conclusions and future work. Our hidden inheritance technique provides an alternative approach to use the unsound static types of TypeScript without breaking the language. We implement the hidden inheritance design in STSC built on a commercial JavaScript virtual machine and demonstrate performance improvements on industrial benchmarks and applications. One direction of future work on STSC is to introduce a more sophisticated and powerful type inference. Another direction is to integrate profiling runs to improve the quality of the static types of TypeScript. Thank you.